Hello everyone, my name is Li Fengjin, and I'm glad to present to you our recent work on grounded PCFG induction with images. This is joint work with my advisor, William Schuler from the Ohio State University. So, recent work in grammar induction shows a wide range of linguistic structures and categories can be discovered in many languages with different kinds of typologies. But however, proposed models in these works rely on text statistics only, lacking semantic, pragmatic, and environmental information. But we also know that humans do use these kinds of information for learning, so it would be great if we can incorporate these kinds of information, start to incorporate these kinds of information into the induction models and see whether they make a difference or not. So in this work, we propose and analyze a grammar induction system where both text and accompanying images are used as input. So let's look at the baseline system. The baseline system is called no image PCFG because it does not take any image as input and relies on only text. This baseline word-based model optimizes the data set likelihood by computing by using the inside algorithm to get the dataset likelihood marginalized over all possible trees, and the tree probabilities are calculated through a PCFG, and the probabilities inside the PCFG are estimated with neural networks. For example, the probability of a category generating a word is a product of the probability of the category generating a terminal and the probability of that word being the terminal. And the second term can be estimated through a neural network taking the embedding of the category and the embedding of the word as its input. So we can add a visual module on top of this baseline system. So first we concatenate all the syntactic word embeddings into a matrix. And the word embedding matrix is projected by CNN into the syntactic visual space as the syntactic visual embedding. We also encode the accompanying images with ResNet pre-trained with the ImageNet classification task and fixed during training into a visual embedding. And then we compare the visual embedding and the syntactic visual embedding from the sentence and add to the grammar induction loss and jointly to optimize both of them. And this is how this is what the image pre-PCFG model works. Finally, because we think that the ImageNet classification task is not necessarily suitable for extracting information important to induction, so we want to train the image encoder along with the rest of the system as well. So we add on top of the model an image decoder and try to decode the visual embedding to a image, and the image encoder and decoder are jointly trained with the rest of the system with a reconstruction loss, which compares the original image and the reconstructed image. So the objective becomes a summation of three parts: the induction loss, the loss between syntactic visual and visual embeddings, and the loss and the reconstruction loss. And this model is our full model called image PCFG. In terms of the experiments, we have a series of baseline models that we compare with, including the no image PCFG and image pre-PCFG models we propose in this work, as well as PRP and OSTM models, which don't take images as input, and VGNSL, which relies on images to produce syntactic structures. It is worth noting that VGNSL model requires heuristics like head final bias and external resources like fast text embeddings for it to outperform the models without the baselines without visual information. So the data sets that we use are also there are two main data sets, MS COCO and multi30K. MS COCO is in English and the multi30K is in English, German, and French. We also translate the English parts of these two data sets into Chinese, Korean, and Polish, which the reason will be explained later. Finally, for evaluation, we report unlabeled F1, which is popular amongst grammar induction work. Also, a newly proposed labeled evaluation metric called recall homogeneity, which measures both the unlabeled recall of parses as well as the homogeneity score of between the gold labels and the predicted labels of those recalled spans. Right, so on the standard set, MS COCO, MS30K English, German, and French, we first, the proposed models in this work all perform better than the baseline system from the previous work by a large margin. But amongst all the proposed models, the no image PCFG actually performs the best, showing that there is actually no effect for visual information on the grammar induction on those languages and data sets. Our hypothesis is that despite it being surprising, we think that when learning languages with high frequency words highly indicative of syntactic information, such as determiners and prepositions and auxiliary verbs, the visual information does not help because the inducer can get most of the information from the text statistics only, and the visual information does not really add on top of it anything extra. But if we find languages where there isn't many high frequency words which are indicative of syntactic information, then we may see a positive effect of visual information on induction. And this is exactly the reason why we chose Korean, Polish, and Chinese as our candidate, a second set of candidate languages to look at. And we translate them and look at the parsing accuracy on these languages, and we can see that on the majority of those datasets, image PCFG model does outperform the no image PCFG model. And if we plot the difference between these two models and how wide the distribution of high frequency words is, and we can see that there is indeed a positive correlation between these two variables. Now, so if images do help induction as some kind of proxy to semantics, then we think that there could be three different ways that the images help it. So the first way is that the models may be able to find clues for categories of linguistic units from visual information, such as noun phrases or parts of speech. For example, for the sentence, for the word spaghetti, if it co-occurs with a plate of spaghetti in different images, then the model is able to find a correlation and say that this particular word is spaghetti. It has some kind of tangible tangibility value, and then based on that, it may be able to come up with more accurate lexical categories or phrasal categories for the words. And for this hypothesis, we look at the parts of speech and noun phrase accuracies for different for models with or without images to decide whether this is supported by evidence. Secondly, the model may be able to find clues for solving syntactic ambiguities which may not be solvable with text only. So for the sentence "Mary eats spaghetti with a friend," there could be two interpretations based on its syntactic structure. If the prepositional phrase "with a friend" goes with a high attachment structure, then the sentence meaning can be represented by the first picture, showing that the friend is a company to Mary. But however, if the syntactic structure of the sentence is a low attachment structure, meaning that the "with a friend" is modifying spaghetti, then the meaning of the sentence can be represented by the second picture, which shows that Mary is eating spaghetti with and her friend, just like something an ingredient or an condiment to the spaghetti. So in order to test this hypothesis, we use a propositional phrase attachment disambiguation task to see whether models with visual information can have higher accuracy in PP attachment task. Finally, the models may also find clues for unseen words in ambiguous syntactic environments. And for this, we look at, add UNC symbols into the test set and look at the parsing accuracies from the models with or without images. So we look at the POS tag homogeneity and NP record scores with and without visual information to see if visual information has any impact based on the first hypothesis of benefits from visual information to induction. And on POS tags, we don't actually see anything, meaning that the quality of the POS tags induced by models with or without information is the same. But for noun phrases, we can definitely see that there is a difference. And more importantly, noun NP recall or multi-30K German, French, and Chinese are actually higher with the visual information than without, which is in contrary to the RH performance, the overall RH performance trends on the whole test set. Second, let's look at the PP attachment disambiguation task, which is inspired by the second benefit, where visual information may provide important clues to syntactic ambiguity. The task uses a dataset from Nakashole and Mitchell 2015. The test items generally have 5 words: hotel, caught fire during storm, and we'll look at whether fire during storm or caught fire is a constituent in the best parses. But for this sentence, hotel caught fire during storm, because it's high attachment structure, then caught fire should be a constituent in the best parse instead of fire during storm. And we can see that the accuracies with models trained with visual information are higher than the models without, contrary to RH performance trends. And finally, for the UNC set, we add UNC embeddings into the test set and report RH. And on the Chinese data set, the image model wins where it previously lost on the overall evaluation. So the key takeaways. First, visual information can help PCFG induction on languages where statistical information from text is not reliable enough. Second, experiments show evidence that visual information help with phrasal labels, ambiguous syntactic structures, and unknown words in the induction process. And finally, PCFG induction models are strong baselines for research of constituency tree prediction. Thank you.